Hello, welcome to CM Videos. Have you ever thought about when you're trying to design an experiment if you're actually doing it right? This is something that a lot of times students ask me, what do I need to do with my experiment? Am I setting it up properly, right? And these are kind of questions that maybe as a student, as a researcher, as someone working in an industry, you may be interested in those kind of issues. And so I'm making a series of videos on modeling of experiments, especially how you can generate numerical insight into those sort of issues around your experiments. And the focus for today's video is on shear testing design. And we're picking up a really exciting type of shear test setup, which is called the Arcan Fixture. So if you're interested in an Arcan Fixture, which looks like this, and the kind of result that you generate from this, which are these kind of simulations where we look at tensile, compression, and a combined loading, then you have come to the right video. So let's sit back and relax as we get started with this modeling. Okay, so the outline that we're going to be working with this video is, first I want to introduce a little bit around the issue of shear testing. What is the introduction of shear testing? And then we'll now look at how do you set up actually your shear test setup within ABAQUS, so that at the end, after running simulation, you can then obtain that numerical insight you're really interested in about your test setup. And then of course at the end, as engineers, we're always interested in stress and strain data, mechanical engineers. So we'll be looking at the stress and strain data from our simulation, and also the comparison of effective properties resulting from your test setup. I've got to say that for the effective properties and the plotting of stress strain data, this will be the subject for a different video. So please do check out for that different video. We are going to be dealing with the first two, and then the other two will come up in a different video. If you're really interested in jumping ahead, look at the stress and strain and effective properties, then please look in the card. When I make the video, I'll be putting it up in the card so that you can see and explore a little bit more what that is about. So that's what we're going to be doing with this video. So if you look at the introduction to shear testing setup, and I really want to give a fundamental understanding, and I apologize if this is very elementary for you, of what shear testing is. So let's consider that we've got our specimen. It could be any kind of specimen. Of course, it will have a certain configuration associated with it. And we'll talk a little bit about the configuration of the specimens later on. And so the principle of shear testing is that there has to be a part of the specimen that has to be anchored. So what we see here is the anchored base of the specimen. So this may be connected to your test equipment, where if the specimen is fixed, it's not able to move. And then there is also a fixed, secure part to this test setup, like we can see in this. And then the next thing that we can notice would be a part of the specimen has to be held and pushed. So what we see here is a force or a displacement will apply onto the top part of the specimen or another part of the specimen to push it forward. And the effective loading condition or boundary condition for that is that it has to be some kind of a roller support that pushes the domain outward. So this is a classic design of a shear test setup. Now, what happens? So the top end would have to deform given this sheared shape to our specimen. So we have a specimen that looks like in shear, creating an angle at this point, which is the angle of the shear specimen during the deformation. So this is what a shear test setup has to be. Whatever kind of test setup you're using, it will always have this structure. Okay, now, so what are the different type of specimen design or types of test setup you can get? And this is a very common one. It's called double notch shear specimen. And essentially, you could have a design that looks like this. So it's got a notch here and it's got a notch at this other point. So those two things are notches, and this is a U notch because if you look at the shape, it looks like a U. And then you also have a V notch, which in this case, a V notch specimen. So this second specimen is used in what you call the IOSFA school test setup, but I'm not talking about that for now. This could be the subject of a different video in future. So if you think about these two, they are good examples of a shear test specimen. And in terms of what we talked about previously, we need to have a deformed profile for this specimen. So what you see here is how it will deform as you begin to test it. So the base here is anchored, the top end is moving. So what this will mean is that this part of the model would have to be anchored, and the other part would have to be in motion to create the shear deformation. So the deformed profile will still be this deformed parallelogram. The same thing will apply here. So one part of this specimen, your specimen would be anchored, and the other part will be in motion. But we're not talking about these two types of specimen in this video. So let's look at what we are really interested in, which is the Arcan Shear Test specimen. I'm really interested in the Arcan Shear specimen because it's designed for thick specimens, and you can do a whole lot of interesting things from your shear test setup, and I'll talk a little bit more about that later on. So this is a classic design. Some people call it a butterfly specimen because the shape of the specimen looks like that of a butterfly, and that's what the Arcan Shear Test specimen look like. So again, what you would expect that there will be a deformed profile. So the left hand side of this specimen will have to be fixed securely, anchored securely, and the right hand side of the specimen will have to deform, so that the back end becomes the fixed end and the front end, or the right end, becomes the part that are in motion. So this is what we want to do when we're interested in doing a shear testing for an Arcan shear specimen. So we're going to be using this in demonstrating numerical insight associated with our shear test setup. Okay, what about the fixture? How do you actually do this? The fixture for doing this is something that looks like this. So I've taken this picture from a publication again. So it looks like this. So what you have is, like I said, this part is going to be fixed. This part is going to be fixed, and the other part is going to be in motion. So this end and that end go into the test equipment, so that as you begin to pull it out, the one end is fixed, the other half is in motion, is able to move. And then the region around here and there are regions where this Arcan fixture is broken, and so you can always pull it apart at that point. The other thing I've got to say is that right in the middle here, you've got the test specimen. So this is the test specimen that we're interested in testing, and when we test it, the objective here is to pull it so that you end up having a shear deformation like I showed previously. So, and this could be the way it would look like during the test setup. Okay, so what are the possible loading types that we'll be using in creating shear deformation and other kind of deformation for this Arcan shear test setup? And this is really where the beauty of this shear testing arrangement comes in, because what you end up having would be a tensile deformation. So basically, when you connect the Arcan shear test and you pull it, horizontally, you are creating a tensile deformation in this test specimen. Now, if you move your testing arrangement and you pull it in the other direction, so you end up having a shear test setup. And then you could even have other test setup, which is a combination of some tensile and some compressive testing, which is what you see in this point. So this case will be a tensile pull plus a shear deformation. And then finally, on the other side, you have a compressive plus a shear deformation, so which is what we see here, a compression plus a shear deformation. So the Arcan shear test is a really beautiful test that you can use to do different type of loading, a tensile test, a compression test, and a combined loading in order to test materials, especially composite materials, to generate a failure envelope associated with them. Okay, so the case study obviously that we're going to be using is the details of the test material is given in this picture. So we're going to be modeling based on this detailed specification. And the material that we're going to be using for this test is PVC, polyvinyl chloride, and the elastic properties are given. And in particular, these properties are, the PVC is a molded, not an extruded material. And I've got the properties from this website, which is mathweb.com. In terms of the different case studies that we're going to study here, so what we have first is a case 1 tensile deformation, a case 2 shear deformation, case 3 tension plus shear, and case 4, which is compression plus shear. So these are the kind of simulations that we're going to use to illustrate the beauty of the Arcan shear test setup and to get insight from our simulations. So we're going to go into ABAQUS and set up how this model will run. All right, so we are here in ABAQUS and we're going to set up this Arcan shear test setup. So if I just show you, this is a test specimen that we're working with, and it will have dimensions of 120 by 120. So we'll start with that. So here in ABAQUS, if you click on the part module, so I'm going to call this Arcan Specimen. So it's a 3D system. It's going to be extruded, and we're going to continue. So I'll first create a box. So 170 by 152 by 152 will mean minus 76. So I'm making the system to be central, 76, 76. So this becomes our block, which represents the perimeters of the specimen. So what we're going to do next is, let's draw a construction line in the middle. So I'll draw a construction line, and then I can draw one of the angles, and then draw the other part. So what I'm going to do is basically to do two sides of this butterfly shaped specimen. So let's dimension it to find out, so that, because according to the diagram, the angle of separation between these two parts has to be 90 degrees. So we've got that. And the other thing that we need to be aware of is that this region, there's a fillet here, which is 2.54. So we apply a fillet there. So 2.54, select the first part of the fillet and the second part. So this is the material that we're looking to get. Okay, so the other thing that we notice is that the separation between one end of the fillet and the other end is 31.5, 31.8. So if we divide that into 2, we get 5.9. So I'm going to translate this. So I'm going to move this bit, these two, with the fillet, excluding the, okay, from wherever it is currently located, which is this point, to 0 on the x-axis and minus 15.9, which is the angle of the distance from the center line to that point. So this is what we get here. Okay, so now I'm going to also draw a construction line in the middle of the specimen, okay, at the 0 line. Now I'm going to create a mirror image of this down part. So press and hold here and slide onto the mirror image. So we're going to create a copy of this mirror image. This is our line, and then these are the entities that we want to mirror. Done. Okay, so you could see now it's created this butterfly shaped specimen with a separation of 8 millimeters in the middle, and every other thing kind of will come together. So I'm going to just trim off all the other bits that are not essential for us to use. So we'll trim off all that by clicking on them. And now, so the other thing that we need to do is to create the circles. So what we know first with the circles is that the first circle is 38 meters from the center line. Okay, so we do that. So I create a circle. It is 38 meters from the center line. So 38 and 0 is the origin of the circle. All right, so it's somewhere around there. And if it's going to have a diameter of 5, so that the radius would then be 2.5. So if we check again, so the radius will be 2.5. So 38 plus 2.5 will mean 40.5 and 0. So that's the circle. So we can do the next circle. The next circle we know is going to be a distance of 60 from the center line. So 60 and 0 and 62.5 and 0 will give us those two circles. All right. So the other thing that we know is that in the vertical direction, the first circle is 90 meters up and 90 meters down. So what do we do? So we click on that circle. So at the 38 point, so 38 and 19 on the y-axis. So 40.5 and 19. So that's the coordinates of that. So this one would have to be at a distance from here of 38 and 60. So 38 and 60. So 60, 38, and then 62.5, 38. So those are the values of that. So we have that. So what we're going to do is to do a mirror image and create a copy. So we use this mirror line. Okay, that's fine. And the entities that we want to mirror are basically those two entities. Done. So it mirrors them to that point. So this is okay. So I'm going to delete these two construction lines because they're a bit confusing. And then we will now apply a proper construction line in the middle, which will be this one. Okay, right. So now we also need to mirror this other image. Maybe we can delete this other construction line. So we mirror this one. So again, I create a mirror. I want to create a copy. This becomes my mirror line, and I'm looking for all these entities that are here. Done. So this way we have our structure created. Okay, so the structure is created and it's effective in the way it should be. So we click done. So how much are you going to? So this specimen is 10 meters thick, 10 millimeters thick. So that's the shape of our specimen. Okay, so we now need to create a partition to create the gauge section. So click on that. So this is the face I want to partition. Done. And then I click on the edge here. So it gets me into this window. Then I click the rectangular button. So I zoom in. So I want to start from that corner to this corner. So this is basically my partitioning face. So and then that partitions that only that face. But then we need it to partition all the way to the back. Because if you check at the back, there's actually no partition. So it's only the front face that is partitioned. So what we then need to do now is to make sure that we can extrude this partitioning face. So we'll press and hold on this button and select this one, which says partition by sweeping or extruding. Okay. So individually, so I'll select that, pressing down shift. So I've selected all that and click done. So I want to extrude along this edge. And I create a partition. So now at this stage, what you'll notice that you have the partitioning all the way through. So if I go to the meshing module, click on that. So I could mesh with this, size of 5 across board, but we clearly need fine meshing around this gauge section region. So what we're going to then do is to use a seed edge. So seed edge. So I'm going to select those edges. Okay. So how many seeding are we interested in doing here? So by number, so maybe we can do 10. So there will be 10 seeds on those edges. Okay, so we've done all that. So we can then decide on how we're going to mesh this domain. So it's going to be hexahedral, swept across the domain, medial axis, minimize mesh transitions, and then I could mesh. So this therefore gives us something that looks like a good mesh. If you look at the central region, you could see that there's a real nice symmetry in how this domain is showing. So this is fine. So it's a good mesh, and the center region is where we're going to have to extract properties that we need. So the next thing that we need to do while we're still at this is to create a sort of sets. So I'm going to call this my gauge section set, and it's going to be based on the central region. So I'll just draw a line in the central region, and then I check it's selected correctly. That's fine. So the other set, I'm going to call this my left holes. So the left holes will be these holes that are here. So you select them, pressing down shift, because we're going to use them to apply our loading history on this domain. So we need to know where they are. Okay, so that's the left holes. So we now need the right holes as well. So we'll basically press down shift and select all the right holes. So all that's selected, and just to make sure that everything is fine, so we'll go to sets. So you could see the left holes are clear, the gauge section is clear, and the right holes are also clearly selected. So, and then we've meshed the domain, and we're happy with the domain and everything that we need. Now let's do the properties. So the material that we are using is PVC, and PVC has elastic properties of 3.24, each power 9, and 0.4, and the plastic, the yield stress was 52, e to power 6, and 0 on that axis. So that's what we have, and then we can create a section. So PVC section. So the PVC section will be that, and then we can associate, do a section assignment, select everything we've got in the model, and then assign it to that. So we've got that. Under the assembly module, we create an instance of the model. This is fine. And then our loading history. So this will be loading step. So we can then think about the boundary condition. So what I'm going to do is I'm going to say, okay, fixed, secure, back, because with a shear test, like we said, there has to be a segment that is fixed. So this will be that way. So, and it's going to be based on the left holes. So if we highlight that, so these are the left holes that we're going to fix secure, and I'm going to fix it in all possible directions. Okay, in all possible directions. So basically we have it securely fixed in all possible directions. It's meshed, and we're happy with everything. So what I'm going to do here is I'm going to rename this model and just call it Arcan Shear Setup. Okay, and Arcan Shear Setup. So if we now copy the model, and then we can now call this tensile. Okay, so let's do a tensile test simulation. And what does a tensile test? So we go back to boundary condition. So this will be my loading tensile load. Okay, to be a displacement, a loading step associated with what we're trying to do. So it will be on the right holes that we need, and it would have a load of 15. The overall length is 152. So 15 should be okay for 10% strain. So we apply this on this domain, and then if we take this off and put it here, so you can see what we're saying. So now by applying this load, you're ready to pull the system apart to create a tensile deformation. So we can create a job for that. So something we need to do is to create properties that we need to be able to run the simulation. So history properties. So what we call, so I'm going to call it, okay, main history output, something like that. So these are the history outputs that we need for the setup, and it will be based on the set of the gauge section. So for the tensile test, we're looking at S11 and E11. So the formation in the stress in the 1 direction and the strain in 1 direction will give you the stress that you should really look out for. Okay, so that's what we needed for the test case. So now if we use the same and now say, okay, I'm going to copy that and then have a shear case. Okay, so for the shear setup, everything will be the same except that our load will now become a shear load, and with being a shear load, it will have to move from the 1 axis to the 2 axis. Okay, so you end up having a shear deformation. One back end is fixed and you're shearing securely at the front. Our history output will obviously be different. So the main history output will no more be those, will be the shear values E12 and S12. So these are the strain in the 1-2 plane and the stress in 1-2 plane. So that's that, and then we can create a job for it and we'll call it Arcan Shear. All right. So the other cases that we're interested in, so let's do again another tensile case copy, but this one will be tension and shear. Right. So with the tension and shear, it's a combined load case. We'll go to our history output. So our loading will be a tension and shear load. So what does that mean? So a tension and shear load means we'll have one and also on the y-axis as well. So if we look at it from the side view, so you're pulling as well as shearing at the same time. So it's a combined load case scenario. And in that respect, our history output would also have to change. So instead of just the 1-1 values, we also need the S1, E12, and S12 values. Okay, so that's what we need next. And that's the Arcan Shear. So if we then do a copy of the same Arcan Shear for tension, so we can now do a compression case. So this is now the Arcan compression. So our loading will change. Our loading will not just be a tensile case, it will now be a compression case. And what does that mean? We are only changing the 1 axis into a compressive direction. So if you look at it again, so we are compressing as well as shearing at the same time. Nothing will change in terms of the history output. The history outputs will remain the same. So we are tracking the 1-1 values and the 1-2 values. So we can then go ahead and set up the Arcan tens shear. So this is a tensile shear case, and then the last one will be Arcan shear. So compression shear. So again, everything is there. So what we now need to do next is to run them. Okay, so we've submitted all the jobs they ran, and we got the simulations ready. So here is the first instance, which is a tensile test case scenario. So if we do the animation of that, stem is being pulled in tension in a nice homogeneous way. So it's being pulled in tension, and the region in the center line here is a region where you have the significant deformation. So like you know, with Arcan Shear Test, the holes are really the points you use in holding the sample and also applying loading on the sample. So there's a lot of stress history around the loads, which is expected. And this is why if you haven't aligned it properly, for very brittle materials, there can be cracking happening around those holes because they carry a lot of load. So, but this is what we see, with this tensile specimen. If you look in plane through the thickness, you could see what's happening here. So there is a bit of shear deformation, necking in that region as the sample thins out and ultimately will fall in tension. So if we have incorporated a damage model to this system, you will notice it falling in tension, and that's what we see in this case. So if we look at the plastic strain will give you a similar kind of behavior. There's a concentration of plastic deformation in that region, and so failure will definitely happen in that gauge section. So what about the shear specimen? So if we move on to the shear specimen, so again, you have some interesting results as well. So in the main, there is a bit of stress concentration or shear domination around this middle. Remember, this is a von Mises stress. So if we move on to the S12 plane, 1, 2, so this is stress, shear stress data. And then if we to animate this simulation, okay, so you see there is a shear deformation on the system as it shears across until eventually it fails. So this is what we want. We want this kind of behavior as the system shears. By constraining the material in the way we have done, we're able to enforce a shear deformation concentrating in the middle. So that means if we extract the history of stress in that node section, it is a history actually of shear, in plane shear for this material. So if we look at the von Mises stress, again, it's a different display. Again, what you notice also is that there is a lot of stress concentration around those holes, which is important because that's again where you get to see failure happening. So tightening the Arcan shear fixture properly really is important to ensure that there is no lateral drift, and then those holes will not form sources of crack to this cracking through this domain. So that's what you will notice with the shear test scenario. So let's look at the other case, which is the tensile and shear combined. So tensile and shear combined. So again, if we look here, so what we see here, if we then animate it, would be a system that is not only shearing, but is also pulling apart. So you could see there's a shear deformation, then after gradually the tensile deformation will start coming in. So as it pulls, there is a shear tensile deformation as the domain begins to pull. So the original stress history that you will see somewhere around here start opening up. So if you see what's happening, the region in red start opening up as it's being overtaken by the tensile deformation. So it's a combination of shear and tensile deformation happening in situ. So if we then move on to, let's say, S1, you could see the size of the domain. The stress in the one direction is about 40.4 megapascal, and the stress in the 1-2 plane is about 25.4 megapascal. So there's a significant combination of stress from the two axes. And this is what the combined loading scenario is looking to explore. So what if when we go to the compression and shear, so if we go compression and shear combined, so you get a similar kind of behavior. So if we animate this domain, this kind of result, so what you see is not only just the normal shear deformation, but then there is a compressive effect. So the system starts collapsing on itself, and then there's a compression effect. So if, again, you decompose those two stresses, so in the one direction, what you notice in the domain here is at 25.42, minus 65 in compression. So the dominant stress in compression is minus 65 megapascal. While in the shear plane, you will expect what we had before, 25.5, 25.4 megapascal. So this is the effect you will see, a lateral compression of the domain, and as well as a shear compression. So, and using the same Arcan shear test setup, you can actually do a lot of combined stress loading in order to be able to populate points on a failure envelope to get values that will help you generate a failure envelope. Okay, so if you put all of them together and then do the animation of them in terms of von Mises, so you could see what's happening with that. So you see the dominant tensile deformation, the dominant shear deformation, tensile and shear, and tensile and compression in all these cases. So if you then look at the plastic strain across, nothing exciting to see there. So you could look at S11 for all the domain, you get slightly different behavior, and S12 for all the domain, slightly different behavior. But the summary of all that is really that you could generate some really interesting insights by simply looking at an Arcan shear test setup numerically in this way and exploring the result. This is just for the first part. So in terms of plotting stress strain data and then generating, let's say, a failure envelope from this kind of simulation, this will be the subject of a different video which will be made available here. So please do look out for that. And so if this is the kind of content that you like, please do subscribe to this channel so that when contents like this are made, you'll be the first to see it. So please do look out for the video here, which is about how you can set up this model in terms of extracting stress and strain data from it, as well as maybe using that to obtain a failure envelope. Thank you very much and see you in the next video. Bye.